Here's what you end up with when building your first 2D platformer game using the Godot tutorials on our channel. Over the course of those 10 videos, we show how the nuts and bolts of a simple game come together to create a basic 2D platformer. The project is running in Godot Engine 4 and uses GDScript. It'll be available on GitHub soon. If you want to see more microgame tutorial video series like these, be sure to subscribe and drop us some comments. Maybe a twin-stick shooter or a puzzle game? How about a simple RPG adventure or a mini tower defense? What do you think? Here's what to expect from the series. If you'd rather get straight into the first episode, feel free to jump ahead using the chapter markers. This is my attempt at jamming as many little pieces of Godot fundamentals into a simple framework for a 2D platformer. While I have no plans on taking it any further, it could be improved and reworked into a Metroidvania game or similar platformer genre. If nothing else, it will be a great learning tool for those who are new to Godot 4 and want to get a simple game up and running. There are plenty of other devlogs and tutorials out there on building Godot games, so I'm going to focus on the nuts and bolts as they apply to making a basic platformer game, and I'll be highlighting those important pieces of Godot that are used in various parts of the demo game and code. While not necessary, to get the most out of this series, some prior knowledge of Godot or game development concepts would be helpful. This project was originally written in Godot 3.5 but was recently migrated to Godot 4 specifically for this series. It uses the built-in GDScript language. I'll make a few call-outs on common hurdles I encountered during that migration, but the focus is going to be on the new shiny 4.0. Before we begin, keep in mind I'm not a graphics artist and my programmer art can and will be absolutely terrible. You won't find advanced shader code, large animated sprites, optimized frame rates, or speedy algorithms, or any other eye candy techniques in this series. We'll focus on the building blocks of gameplay. The components of this game are not intended to look visually stunning, but rather they're meant to showcase the logic and moving parts of a Godot game in action. I hope that makes sense. If there's enough interest, I might package up this project and place it on GitHub for subscribers to check out. However, the music and audio I'm using are licensed for use only on YouTube, so I won't be providing those assets. The series is broken down into 6 easier-to-digest episodes, each one building on the episode before them. By the end, we'll have a mini platformer game running in Godot 4, and you'll have a good understanding of how all the pieces fit together. We'll start by doing some prep work like setting up Godot's project settings, looking at the PS4 DualShock controller, and configuring it in Godot's input settings. We'll be explaining the few global objects in the project, and finally we'll do a quick review of the folder structure. Then in episode 2, we'll check out the 3 main Godot scenes used in the project. These are the game scene, the player scene, and the level scene. There are more scenes, but these 3 make up the base of the game logic. Using these scenes, we'll learn about the core game components like startup, pausing, and scoring in the game. Next, we'll take a quick tour of the UI and the tile map elements of the game in episode 3. We'll use Godot's canvas layers to stack different drawing layers like a HUD and scrolling backgrounds. And we'll use a tile set and tile map to create the level that we'll go to in more detail in a later episode. Episode 4 is a big one. We'll dive deeper into the player scene, including covering common mechanics such as stats, movement, collision, the state machine, the camera, lights, and sound. At last, in episode 5, we'll break down the centerpiece of the game framework, the level scene, where we'll dive into details on the tile set, item upgrade placement, enemies and boss, hazards, and background music. At the end, in the final episode, we'll talk about some of the ideas that could be added to the game relatively easily. Things like a start screen, a replay button, adding saved games, adding a mini-map, adding new tiles to the tile set, or even adding new weapons, enemies, AI, and new bosses. And so, with the intro out of the way, let's begin. I always like to start by looking at the project settings. This is where several important settings are found in various tabs. On the General tab, we have the application, display, and layer names that we'll look at in more detail. On Application Run, here we'll tell the game the first scene that runs when the game is started. In this case, the game scene is what we want. In the Display Window Viewport Size setting, here we'll set the window mode and viewport resolution for the game. The demo will be windowed to allow us to easily watch any debug output in the editor while the game is running. In the Layer Names 2D Physics section, here we'll give the names of the physics layers in the game. This is much easier than trying to remember the layer numbers. The layers in the demo are the player, the tiles, the player triggers, the bullets, the enemies, and the hazards. The player, this one's pretty easy to understand. The tiles, this one represents the hard tiles in the tileset level, things like walls and floors. The player triggers, in this layer, are all the trigger points that the player can interact with, like picking up items or toggling switches. In the bullets layer, bullets go zoom and impact layers like tiles, enemies, and the player. The baddies layer is where the monsters and bosses reside. Like the tiles layer, the hazards act as floors and walls but will damage and stagger the player if they touch them. On the Input Map tab, we'll configure input keys for the game. We'll set up keys on the keyboard and also set up the buttons for a PlayStation 4 controller. Most of these buttons are given friendly names, and so this is easier than it used to be. Most of these input actions are self-explanatory as to what they do, and we'll see a few of them in code in a later episode. Next up is the Auto Load tab. The game will use a globals script which allows any part of the game code to access important data objects quickly and easily. To enable the feature, we have a single file enabled on the Autoload tab, globals.gd. We'll look at the globals in more detail in the next episode. That covers the project settings that are important in the game. Now let's take a look at the file system. The game is organized into various folders. The root resource folder contains the main game scene, globals, and matching scripts. All other scenes are stored in the scenes folder. The graphic and audio assets are stored in the assets folder. Besides the game screen and globals, all other scripts are stored in the scripts folder. And this folder is broken down further to make things more organized. Scripts for enemies, projectiles, the state machine, and player triggers all have their own subfolders. And that covers the prep work for the project. It should give you a good map of where the important game level settings and assets are found in the editor. Next up, in episode 2, we're going to look closer at the 3 main scenes in the game in the main game loop. Hi there, welcome to episode 2. Let's look at the 3 most important nodes used in the game. These scenes represent the core game logic like startup, spawning the player, pausing the game, and showing the player their time score after winning the game. The first is the game scene. Even though the scene itself is not complex, it is one of the more important because it's responsible for managing all other parts of the game while the game is running. It is the scaffolding that all of the game logic runs on. We'll take a look at the game scene's code in a moment, but let's look at the tree structure of the scene first. A game scene consists of 2 children nodes, the player instance and the level container node. The player instance is what the player will control in the game, and we'll dig into that scene in much more detail in episode 4. For now, I'll make 3 callouts for this player node. First is this icon here. It tells us that this node is an instance of a more complex scene. We can click it to view the full scene in more detail. Second, the node type of the player scene is character body 2D in Godot 4. Previously in Godot 3.5, this was known as the kinematic body 2D. And third, this player node will be moved to a different location in the node tree when the game starts up. It will be moved to the level container node. The second child node is that level container. This is where the game data will exist during runtime. It is broken down into several canvas layers that we'll draw on during the game. For example, we have a layer for the pause screen, one for the HUD, and one to store the level's tiles. We'll also keep the parallax background in the level container. In the next episode, we'll provide more details on the canvas drawing layers, and in episode 5, we'll break down the level scene even further. Okay, so we want to see some code for the game scene. First, we need to know about the globals used in the project. It can be opened using the file system panel in the editor. Globals allow us to access critical data from anywhere in the game without having to know the exact location of that data in the node tree. We'll use the following globals set up in the globals GDScript. The game object is our link to the main game scene. We'll use this anytime we want to quickly reference the main game scene and data. The link to the player's camera will allow us to quickly change the viewport during the game. We'll have links to the various drawing layers so that we can draw to those canvases from anywhere. And we'll have a true-false flag to represent if the game is paused or not. And we'll assign all of these globals to the correct data and locations in the tree when the game starts up. With the globals out of the way, we can now look at how the game starts up and how we score the game. Our game scene is using the script game.gd. It can be opened by using the script editor at the top, or by clicking on the script icon next to the game scene in the scene tree at the left. At the top of the script, we have 3 variables. The first 2 store the time the game has been running. We'll keep track of when the player pauses the game, and we won't count that against the player, so we'll have 2 time variables. The third variable holds the level scene that we want to load. We'll use Godot's preload function here, so that we can create the scene later using the instantiate function. We can easily swap out different levels during development by changing this preload. In addition to the variables, there are a few functions to see. In our ready function, we assign all the globals to their respective nodes in the node tree. We'll also create the new level instance using the preload level from before, and move that new level instance and the player instance into the correct layers in the game tree. Finally, with the nodes in place, we can initialize the level's trigger points and start to level. In our process function that runs for every frame tick of the game, we'll keep track of the total time the game has been running. That way we can show their time total when they win. In this demo, we also print that time out to the debug canvas. This function also handles the player's pause feature of the game. It allows the player to pause and unpause the game, and it has several effects, the main one being that the time counter doesn't increase when the game is paused, and will only resume when the game is unpaused. Pausing in Godot is an interesting design. Because the game is a tree structure, we can decide which parts of the tree branches are affected by pausing the game engine. We do not want to pause the entire engine. By using a combination of the process modes, always, pausable, inherit, and disabled, we can pause parts of the game, like the player and the level, but leave other parts, like menus or the actual unpause button, unpaused. Notice how the top-level game scene process mode is set to always, but the player scene mode is set to pausable. When the game is paused, the code and logic on the game scene will continue to run and it will not pause, but the player scene will be completely paused and any code in it will not execute. Similarly, the drawing layers also have their process modes set to allow the level, including things like enemies and bullets, to be paused, but leaving the pause screen and the HUD layers active. If we did not set up the process modes this way, we'd find that once we pause the game engine, the player would not be able to unpause the game because the engine would have stopped accepting input. Finally, in our handle pause function, we check to see if the player just pressed the pause button. If they did, and depending on if the game is already paused, we'll set the global's game pause flag. We'll hide or show the pause screen, and most importantly, we'll pause or unpause the game engine using the getTreePaused property. And that covers the primary scenes in the main game loop with pausing capability. We're going to jump into the player and level scenes in episodes 4 and 5, but in the next episode we'll go over the different canvas layers in more detail. Those layers will help us draw the game's sprites, tile set, HUD, and text messages in the game. Hi there! Welcome to the third video in the series. In the last 2 episodes we looked at the project settings and the first 3 scenes in the project. If you missed them, check out the development playlist. Now, let's look at the drawing layers used in the game. Godot's canvas layers will help us draw the graphics in the game, name sprites, tile sets, heads-up display, and text messages, and stack them on top of each other with the correct vertical order. Canvas layers can be used for many different things, but we mainly use them to keep the game layers and interfaces organized. In the demo, we'll assign a layer value to each of the canvases, and this value will tell us which layers are drawn on top and which are drawn in the background. The layers with the smallest number will be drawn first, and the layers with the larger numbers will be drawn on top. Our first canvas layer, the pause layer, we've mentioned already in a previous episode. This is a simple layer that's displayed while the game is paused. Nothing fancy, it's just a label for now. One thing to keep in mind here is that this layer is not paused even when the player pauses the game. This is represented by the process mode of always in the Node Inspector panel on the right side of the editor. And because we're using that mode, we could easily add a full overlay screen for this pause layer. A screen with a menu of buttons for things like opening the game settings, viewing a map, viewing leaderboards, or quitting the game. You can also see that pausing the game stops the player timer, but still allows the total timer to continue running. The second canvas layer holds all of the heads-up details that overlay in the in-game graphics. We broke down the HUD components even further into 3 parts to make things easier to expand later. The first component is the health panel. This allows us to show the player their important stats like character health at a glance. In this demo, it only displays the remaining health for the player before they get a game over. Later, if we wanted to add more stats like stamina or a mana pool, we could easily add them to this area of the HUD. The second component is a group of basic UI pop-up panels that appear during gameplay. These panels let us display simple text tips and messages to the player, including the in-game messages as well as the game over screen and win screen. This icon shows that the panels are not visible when the scene starts. We'll use code to show and hide these panels, but sometimes it's useful to see the nodes in the editor, so we can turn these on temporarily if we want to see what things look like. We just have to remember to turn them back off. The third component of the HUD, the debug panel, is mostly helpful while developing the game. But for a finished game, it would either be removed completely or made into a setting that can be turned on and off. All of these panels use simple label nodes that print text to the screen, and each can be dressed up and styled accordingly to fit the needs of the game. For this demo, I've set the theme overrides to give the panels a color background and to give some of the text labels some drop shadow. The only additional callout is the message panel, where we have the timer node. This allows us to show this specific panel for 5 seconds before automatically closing the panel. We'll see that code later when we dive into the player triggers in episode 5. Like the pause layer, the various HUD layers do not pause when the player pauses the game, so we have a process mode set to always on this canvas. There are a few exceptions, but most of the children nodes will inherit that process node from this canvas. The next canvas layer is the level layer container. In the editor, it doesn't look like it contains much. However, when the game starts up, this layer is where the player and the level runtime data will live. The entire tile map and all of the enemies, items, and triggers will be here as well. In effect, this is the main container of the game tree where the player actually controls their character in the game world. This layer will actually be paused when the player decides to pause the game. This is because the process mode on this layer is set to pausable. In episode 5, we'll learn all about the stuff that goes into this level layer and its related components and all of the child nodes it contains. The last canvas to discuss here is the parallax background. You can make some really neat multi-layer scrolling backgrounds with this node if you're willing to play around with the settings. However, for this demo, we are simply using the single background image and setting the parallax properties to make it scroll when the player moves their character. We'll simply scroll at different rates for horizontal and vertical directions to get the very simple parallax effect that we want. To do it, we'll open up the parallax background scene using this icon in the scene tree along the left side of the editor. That will open up the scene where we'll find the parallax layer node. On that node, we'll use the inspector to set the motion scale to 2 different values, one for horizontal and one for vertical. That covers the canvases, but before we finish up, I wanted to give a shout out to the artist Anzimas for their wonderful pixel art and asset packs. In this demo, I've used a few of their images from the Gothic Vania Town Pack. You can check them out on twitch.io, and if you're looking for quality pixel art assets for your next Godot game, you might just find what you're looking for. Anyway, hopefully this episode gives you a good sense of the game's canvas layers used in the project. Next, in episode 4, we'll dive into the player scene and the many mechanics and techniques that we use to allow the player to move around and interact with the game world. Hi there. Episode 4 is a big one. Over the course of the 4 parts, we'll look at the player scene and its components, including covering basic game topics like player stats, movement, the state machine, camera, collision, light, and sounds. In this first part, we'll go over the character body 2D class that we use as a foundation for our player character movement. We'll get our first good look at the script and the scene tree for the player object, and we'll focus on the concept of player properties like movement speed and health points. Let's get right to it. Here's the player scene tree. It contains a bunch of children nodes that handle all sorts of things for the player. The focus of this video is the top-level player class and the child player stats class. We'll look at those two scripts in a moment. First, let's look at the custom settings that we can change directly in the editor for the player and player stats nodes. These variables are exported from the class and into the editor using Godot's GDScript export annotation. And we'll see those exports in a few seconds. We've added these custom variables to our player scene. We can make the player start with any of the items in the game if we want to test them out, change the way the camera works for the player, and also change many of the physics engine parameters that we need to make a simple platformer. Each of these can be changed in the editor to see the effects directly in the game in real time. The player stats scene is where we'll store things like hit points, stamina, or a mana pool. To keep the demo simple, we only have a health pool. And here's where you can change the player's max health directly in the editor. If a node has a script attached to it, it will have this icon, and you can click on this icon to open the script in the editor. I won't show a full example here, but you can also use this button to attach a new or an existing script to a node. We already added a script to the player scene. Our player scene is directly based on the character body 2D class from Godot's 2D physics engine. This is one of the easier ways to move player objects around in a Godot game, and it gives us a very useful move and slide function to help move the player around without having to write tons of code. There are other ways to move Godot physics objects around, including rigid bodies and static bodies, but we found the character body 2D to be a good fit for a controllable character and a simple platformer. You can read up more about the character body 2D physics on the Godot engine website. Our player scene gets all of the awesome features that a character body 2D normally gets, but then we also added several other settings to further allow us to customize the way the movement physics will behave in the game. Let's dive into the player scene script and look at some of these custom settings and features. We saw these settings a few moments ago in the inspector, and here they are exported in the player class script. The numbers can be changed and tweaked, but we found that these values created a good place to start and allowed us to easily move the player around with the PlayStation 4 DualShock controller. We also have several switches that tell the game if the player has given an item upgrade or not. When the player picks up the items in the game, these flags will be set to true, or we could set them in the editor to test the upgrades right at the start of the game. We'll look at the bullets in the next video when we discuss collision shapes and detecting collisions between objects in the game. For now, see how we're creating a bullet scene here using the preload function? We'll make clones of this object later to create new bullets on the fly, based on the direction the player is pointing. To keep the code more organized, the player stats like hit points are stored in a player stats class. We'll look at that class in a second. In our onReady function, we'll hook up the player stats signals to our main player class. That way, when the player stats are changed and the appropriate signals are sent from it, our main player class will receive the signals and execute these custom functions here. Godot signals can be used for most anything, but these specific signal examples are because the player is either taking damage, or healing damage, or they're just plain dead with no health left. Signals are vital to using Godot, especially if you need to communicate or send data and events between complex scenes. These damage functions are a good example of how they can be used in your own code. You can read more on Godot signals here. Just a side note, this demo is using the new Godot 4 syntax for connecting signals. We find it much easier to use and more efficient when we need to hook up our own signals. If you're migrating a game project from Godot 3 to version 4, then this is one area where you'll probably need to change due to the syntax. The game loop will process the player scene on each tick of the physics engine in the physics process method. Each tick, the game will check and handle changes to the camera, handle firing the player's gun if they have one, and check to see if the player just used one of the in-game switches or toggles. That covers the basics of the player script. Now we can look at the simpler player stats script. Most games have multiple types of stats that a player must manage. We can add more later, but for now we'll just keep a pool of hit points that has a maximum value of 5. We've exported the max health property so that we can change it directly in the editor. Here's how we handled a simple set of signals that could be sent when the player's health is changing or is depleted. You'll notice in these functions below, we emit these signals when certain events happen. Any game objects that are listening for the signals can run custom code, and in fact that's how the player scene knows when the player actually took damage. The last part of the player stats to mention is the invulnerability frame logic. In many games, when a player takes damage, they become invincible for a very short amount of time. This is commonly referred to as iframes. During this window, the player cannot take additional damage, and may or may not have control over their character. Here's how we created a dynamic timer directly in code to set the iframe window to be about 3/4 of a second. We found this to be a good starting point, and it can be changed very easily. Well, I think that covers enough for this first part of episode 4. In the next part, we'll show how the player scene is drawn to the screen using sprites and animated sprites, and we'll focus on the topics of collision shapes within Godot. Hi there, and welcome to part 2 of episode 4. In this video, we'll dive deeper into the visual assets of the player scene. We'll explore various elements including image editing software, basic and animated sprites, as well as collision shapes, all of which play a crucial role in creating an engaging 2D gameplay experience. Let's get started. First, before we create our sprites, we need to have our assets ready. You can use image editing software such as GIMP, Photoshop, Blender, or any other suitable program to design and edit your image textures. You can also purchase or find tile sets and sprite sets on the internet. I personally use GIMP because it's completely free, and while it has a high learning curve, it has some very powerful features that rival the big names. Image editing software allows you to create and modify visual assets for your game. You can design characters, objects, backgrounds, animations, fonts, and more. Make sure to choose the software that best fits your needs and your skill level. The results of this process are your raw image files that will be used as textures for our game sprites. Now let's explore sprites and textures in more detail. The texture is the underlying image used by the sprite. We use PNG files for our images, but these can be other formats as well. In many cases, these files can contain a single image. However, they can also contain an entire atlas of images contained in a grid. Using multiple images in a single texture file helps manage resources efficiently, reducing draw calls and improving performance. We also use textures that contain multiple images to help run animations, which we'll see here in a few minutes. Those are sometimes referred to as sprite sheets or animation sheets. Sprites are the visual representation of objects in our game. The player, the enemies, the world tiles, the item pickups, and the projectiles are all sprites or combinations of sprites. They're composed of an underlying image texture, which we previously described, as well as various settings to control how to shape and scale the image. Think of a sprite as a picture frame that displays part or all of a texture. In Godot, we'll use the Sprite2D class to put it together. We'll load the texture into the sprite using the inspector. And even though we don't use it here, we can also adjust the region of the texture that will shine through on the sprite. Next, let's delve into the animated sprites and their various components. In Godot, we'll use the animated Sprite2D class to assist with animating our character. We have our move animation ready to go in a texture image named pcanim.png. The main components of an animated Sprite2D are the sprite frames, the animation name to be played, the current frame being displayed, and the speed to play the animation. We'll come back to the sprite frames in a second. We give meaningful names to each animation, making it easier to identify and manage them. For example, in our game we have 2 animations, default and move, which makes using them in code very easy. The current frame on the animated Sprite2D can be changed if we wanted to start on a specific frame. We won't be using it here. And the speed scale controls the animation's playback speed. So what about the sprite frames? Sprite frames represent the collection of named animations that will be used. In our game, we have 2 animations in our sprite frames. The first animation is named default and represents the player standing still with no real animation. We can add a single frame to the default animation using this icon and choosing the pc.png file. Now if we play the animation, we'll see that it's not exactly exciting, being only one frame repeating over and over. So we can add another named animation to the sprite frames and call it move. And here, we'll use this icon to add frames from a sprite sheet texture file. Using this interface, we can use the different settings at the top to chop up the combined image into rows and columns, or just columns in our case. Once we select our frames, those images will be added to our sprite frames for further inspection. We can add more frames as needed. Now if we play the move animation, we'll see our wonderful AAA walking animation. Here's where we could modify the speed scale to adjust the animation to our liking. A value greater than 1 makes the animation faster, while a value less than 1 will slow it down. When the game starts, the player will be in the default animation. In our game, the player's actions trigger different animations. For example, when the player moves, we switch to the move animation. By updating the current animation name and code, we can transition between different animations. This can be accomplished using the play and stop methods like this. That covers the basics of a simple animated sprite 2D. Let's talk about these child sprites. We enable and disable these sprites in code when the player performs certain actions like picking up a shield or a weapon, or when taking damage. In our game, we have several child sprites. These are drawn on top of the animation. The shield and the pistol, these have image textures attached to them. The boots and the key do not have images, at least in this version. And here is a special child sprite with a timer, sprite damage. This sprite serves a specific purpose and appears briefly when the player takes damage. It uses a Godot timer node to control its visibility duration. We'll see more details on how the state machine works in the next part of episode 4. Now let's move on to the collision shapes and their role in the game. Collisions are essential for handling interactions between objects in the game world. We could probably write an entire video on handling collisions and the collision signals, but for now we'll keep it basic and rely on the built-in 2D physics engine in Godot. Because our player scene is based on the character body 2D class, we need to add a collision object in order for the physics engine to work. In Godot, we'll use the collision shape 2D class to give the player's character that hard surface that it needs. The most important property of this class is the shape field, but there are a few other callouts that we'll see in a second. The shape of the collision body defines the player's hitbox. We're using a capsule shape for the player, as it closely matches the character's image, but we could use another shape if we needed to, like a circle or a rectangle. We won't do it here, but you can even add multiple collision shapes to make a more complex hitbox. We'll see that in episode 5 when we talk about the game's boss that has multiple hitboxes. During development, it's helpful to visualize collision shapes. We set a debug color to display the collision shape in the game world, allowing us to fine-tune and verify collision interactions. These can be turned on and off in both the editor and in the game depending on your needs. Now that the player scene has a collision object in place, we can go back to the player scene itself and adjust things further. Collisions between physics objects are determined by their collision layers and masks. In our game, the player's collision layer is set to collide with the tiles of the level. We can and will customize these settings further to achieve many different gameplay effects, but for now, this will allow the player to walk in the game world without falling through the floor. With everything in place, the player's movement interacts realistically with the physics objects. The move and slide function, used in our state machine, will handle the player's movement while considering collisions with the environment like the level's tile map. And that concludes part 2 of episode 4. Stay tuned for part 3 where we'll explore camera setup, the player input controls, and the state machine that manages the various states like walking and jumping. And if you stuck around this long and happen to be developing a Godot game that you want us to showcase on the channel, send us a comment. We'd love to share some of your games and experiences with our audience. Hey there! Welcome back to episode 4. If you're following along, this is the third segment in episode 4. If you've missed previous segments or episodes, check the playlists on our channel. In this segment, we'll look at some core mechanics that make our game character come to life. The camera, the player input controls, and the state machine. These elements will work in harmony to create a movable game character in our 2D game world. Let's dive right in. The camera is a vital component in most games, even 2D games, providing players with a view of the game world as they move their characters around. In our game, the camera 2D node is a child of the player scene. This means it follows the player around, providing the perfect view of the action. This node works like our player's own personal photographer, capturing every moment of their adventure. We can adjust properties like enabled to control whether the camera is active or not, giving us the option to use different cameras if we need to. We'll only use one in this game. We can tweak the zoom level to give the players a better view of the game world. Godot will display the camera outline in the editor if you set the draw screen property here. We can use the transform position property to position the camera relative to the player's sprite. This helps us keep the player in the right spot on the screen. Here, we'll see that they'll appear about 2/3 of the way down the screen with a Y position of -120 pixels. As the player moves around the game, they will always be in that spot on the screen. The level around them, including the world's tile map and parallax backgrounds, will automatically be framed by the camera. Perfect. Handling player input commands is key to creating responsive and enjoyable gameplay. We control our player's movement using a few physics parameters like speed, gravity, jump impulse, friction, and acceleration. These factors determine how the player moves and interacts with their environment. Because our player scene is based on the character body 2D object, we already have what we need here. The heart of moving the character lies in the move and slide function in Godot. This function automatically handles collisions and allows our player to move and slide along surfaces realistically. For our player to face the right direction, we adjust the X scale in code, depending on the player's movement direction. This simple trick, inverting the negative sign on the X parameter, gives the illusion of the player turning left or right. During certain animations, like the stagger animation when the player takes damage, we lock the player's input control. This allows us to control the game balance and prevents unintended actions during critical gameplay moments. For those who prefer using controllers or consoles, the Godot input system supports reading input directly from a variety of gamepads. We already talked about our DualShock PlayStation floor controller input mappings way back in episode 1, but here they are again. Let's look at them in a little bit more detail. We identify the possible inputs by their friendly name, regardless of if they originated from a keyboard or a gamepad. In that way, we can simplify the possible inputs the game needs to support. We'll look at the movement type inputs in a minute. First, we'll look at how the character can activate their offenses in the game. Projectiles add an exciting dimension to our game. The player doesn't start with a pistol, but they can find one in the demo level. We'll look at the item pickups, including the pistol, in episode 5. But let's assume the player has already found their weapon. This fire input is what the game uses when the player pushes the attack button. In our case, when that happens, we create bullets as instances of a bullet scene. This dynamic system allows us to control the behavior of bullets with precision. We'll set the bullet's collision mask to collide with tiles and enemies. We can place the new instance into the game exactly where the character is and in the direction they are facing. By instantiating bullets as needed, and by limiting the number of bullets that can be active at any one time, we enable the player to engage enemies from a distance while adding depth to combat and some basic strategy. As we get into episode 5, we'll explore more interactive elements like switches and toggles. These mechanisms enable players to manipulate the game world in a variety of ways, such as opening doors and revealing hidden passages. We'll use the activate input for some of those mechanisms. Keep an eye out for that episode where we'll dive deeper into those level interaction mechanics. The boost input key allows the player to move faster while running and jumping, but only if they have the Speed Boots item upgrade. Our state machine will automatically detect if the boost key is being pressed, and will give the player an increased velocity during movement when we call the move and slide function. Speaking of the state machine, let's talk about the code that organizes the player's behaviors, the state machine. We store all the state-related code in our scripts folder. We'll go over those files in a second. The state machine is controlled by the custom transitioned signal. This signal is sent when the player's state changes and ensures smooth transitions between different player behaviors and animations. For debugging purposes, we display the current state name in the debug output window. This helps us keep track of what our state machine is up to behind the scenes. We'll use the movement inputs and the jump input to activate different states for the player. A state machine is a common software pattern that simplifies complex behaviors into manageable pieces, or states. In most cases, only one state can be active at a time, making transitioning between states easy to handle. A game can have many different state machines for different purposes. We'll use one just to keep track of the actions that the player is taking and the animations that should be playing. Our player state machine only tracks the current movement state of the player, whether the player is standing still, running, jumping, or in a staggered state. The transition between those are handled smoothly by the state machine. By using just a few base classes, we can easily add more player states while keeping the code separate and simple. For instance, each state for our player coincides with one of the script class files here: idle, run, air, and stagger. The idle state is when the player is not moving, not pushing any input buttons, and is on the ground. When the player is pressing one of the movement inputs, and assuming they are on the ground, they will transition to the run state. If the player presses the jump input and they are not on the ground, they will be moved into the air state. The stagger state is activated when the player takes damage, and it locks the movement controls temporarily and applies a knockback effect to the player. We use a Godot timer node to set the invulnerability and input lock duration for this state. The stagger state itself only lasts a single game tick, but it applies a pulse to the player and bounces them back from whatever hit them. This knockback force is then interpolated over time using a tween object in Godot. And then, the player is immediately moved into the air state as they are pushed back and away from the collision. While the inputs are locked, the player cannot move the character, so they'll likely just fly back in an arc and land on the ground, while they'll move into the idle state while the timer continues to tick down. When the timer is finished, it sends this signal, and we re-enable the input controls for the player, allowing them to move out of the idle state once again. Our state machine allows us to manage each of these states' unique behaviors without clogging up a single monolithic movement function, and it keeps the code organized should we ever need or want to add more states to the machine. And that concludes part 3 of episode 4. We've covered some critical aspects of player interaction: the camera setup that keeps the player in the focus of the action, finely tuned player controls that allow responsive movement combat in collisions, and the intricate state machine that orchestrates the player's movement behavior. If you're finding this series valuable, don't forget to hit the like button and please subscribe to our channel. Before we get into the level scene in episode 5, we have one final video for episode 4 for the player scene. Hey there. Welcome to the final part of episode 4. Earlier in the episode, we looked at some major components of our player scene: handling collisions, drawing animated sprites, and moving the character around using a state machine and a camera viewport. You can find those previous segments on our channel. In this last part of episode 4, we'll be putting the finishing touches on our player scene with some lights and sounds. By the end, we'll be able to add some basic lighting sources, cast shadows with occlusion shapes, and play back music and sound effects. Stick around to the end of the video for a quick preview of what to expect in our next major episode, number 5, where we'll finally look at the level scene and building the game world for our player using Godot's tile map system. So let's get started. First up, let's make music with the simple audio stream player node. This is how we'll bring the game to life with sound. There are more advanced ways to manage audio in a Godot game, but this will give us the foundation we need. Our player scene has these basic sound effects: a jump sound effect that plays when the player jumps and the state machine moves them to the air state, a hit sound effect for when the player is taking damage, a gunshot sound effect for when the player fires their pistol, and the cliche sound of a coin being picked up for when the player picks up items in the game world. The most important setting on an audio stream player is the stream resource property. This is the raw audio asset for the sound. We'll use MP3 files for the stream for our node, but you can use other formats as well. Another important setting is the volume, in decibels, that can be adjusted as needed here. You can also adjust these other settings, but we don't need them for our demo game. If you want to preview a sound, you can click the playing checkbox. This will play the sound from the editor and then turn the checkbox off automatically. An audio asset can have a short duration like a quick sound effect, or they can be longer musical compositions. In addition to the various sound effects we just mentioned, we also have the music that will be played when the player's game over screen is displayed. This works just like sound effects with one minor difference. We set the process mode to always to play this sound continuously even when the game engine is paused, which happens during a game over screen. To play any of these sounds in code, we'll set up some reference variables like this. And we'll start and stop the sounds using the play and stop methods on the variables like this. And that's pretty much it for basic sounds. Once we have those notes in place, it's mostly about when and where to start and stop those sounds from within code. We'll see more sounds when we get to episode 5, but those work the same way as these sounds on the player node, with a few minor exceptions. Next, let's shed some light on the game with Point Light 2D. The Point Light 2D casts light on Go 2D environment, originating from a single point. Our player scene has one of these as a child node, meaning that this light will follow the player around as they move. We can easily position the light relative to the player sprite. There are more light sources in a level scene, but because those are not part of the player's scene, they won't move around with the player. We'll see those in episode 5. There are a bunch of other settings for this node, perhaps the most important property being the texture value. Just like sprites, this is the raw light image that is overlaid onto the scene. It represents the appearance shape of the light. The scale mode simply represents how large the image texture should be. The color of the light can be selected here, and the intensity of the light can be set here. The larger the value, the stronger the light. You can configure lights to affect only certain canvas layers or even Z height layers here. We set the mins way low and the maxes way high to cover a very large range of objects that should be covered and affected by the light 2D. If you ever find that your lights or shadows are not being displayed in your game, be sure to check the layers and the Z ranges are wide enough. The objects to be illuminated must fall between these values. Lights are cool, but the absence of light is just as neat. We'll look at casting shadows in a moment, but for now, take note of this section in the Point Light 2D node in the inspector. This shadow section controls how the light will behave when other objects want to cast shadows by blocking this light. For a light to cast shadows, this enabled field must be set. We can choose the color for the shadow here, and generally this will be partially transparent. For now, we'll keep the filter at PC4 and we'll use a smoothing of 0. You can read up on what those advanced settings do in Godot if you're feeling adventurous. Finally, we must make sure that the item call mask values and the visibility masks on the light node match any objects that we want to interact with shadows. You can make some interesting effects using a combination of all of these masks, but for simplicity, our demo game will only have the single layer to handle lights and shadows. All nodes in our game that cast shadows will have the same call mask layer and light visibility layers. If we simply drop a Point Light 2D into a scene, even if that Point Light 2D has shadows enabled, it won't cast shadows by itself. It will just make everything around it brighter. No, instead we need to tell the game what other objects should block the light. To do that, we'll use a node from Godot called the Light Occluder 2D. This is the node that actually blocks the light and causes the Point Light 2D to cast its shadow colors. By giving an object a light occluder, we can define a 2D polygon shape that will act like a physical barrier and block the light from the light source. Depending on where the light is, how far it is away, and the shape of the occluder, we'll get our shadows cast out onto the game world. Since we don't have any occluder nodes on the player's scene, let's get ahead of ourselves a little and talk about two of the occluders that we'll see in episode 5 in the level scene. Here is an example of an occluder on the in-game hazard tiles. Here, we set the occluder polygon shape using a set of 5 points to form a square. Remember to check the occluder light mask like we mentioned before. With this occluder in place, when the player walks near a hazard tile in the game, the center of the hazard will cast a shadow out and away from the player. Because the occluder does not cover the entire sprite of the hazard tile, notice how the shadow originates from within inside the tile. This gameplay footage also highlights the second example. The tiles in the tile set can also occlude light. Each tile in the tile set atlas can be given an optional occlusion shape. You can find this setting in the tileset editor under the rendering section when looking at a selected tile. Here, you can see that much like our hazard occluder, we'll have a square shape. The main difference here is that the shape covers the entire tile. You can see how that affects the shadows that are cast by the tile set versus the shadows that are cast by the hazard tiles. And there you have it. We've completed our journey through episode 4, exploring the nuts and bolts of the player scene. We've covered a lot of ground, moving the player around, managing collisions, drawing animations and sprites, and now using lighting and sounds. But our adventure doesn't end here. In the next major episode, number 5, we're going to change gears and look at the main level scene at all of its components. That's where we'll build a game world for the player to explore using Godot's tile map system. We'll also look at item upgrades, placing hazard tiles, adding basic enemies, and even a scripted boss battle. Hey there, welcome to episode 5. We're going to jump headfirst into the centerpiece of the demo game, the level scene, where the real fun begins. If you're just joining us, this is a series where we're showcasing many of the fundamental building blocks that are used to create Godot 2D platformer games. This is a beginner series, and we're not creating the next AAA blockbuster game here. It's more about playing with all the building blocks and tools that are available to us and getting to see them in action in an oversimplified but practical way. If you've missed previous episodes, be sure to check out our development playlist on the channel. There's going to be 3 videos in this episode. In part 1, the video you're watching now will explore the core building blocks of the 2D game world, the tile map and the tile set. We'll be using the tile set to form the backdrop of the level, and we'll shed some light on the world with different types of simple lighting and shadows. On top of that, we'll be adding a few more sound effects to set the mood. In part 2, we'll continue improving our game world by adding interactive switches, items, and upgrades. You'll see how we added power-ups and collectible items that enhance the player's abilities. And we'll look at other player switches and adding interactivity to the level and making it come alive. And finally, in part 3, we'll ramp up the excitement as we delve into hazards, enemies, enemy spawns, and the grand finale, the scripted boss battle. We'll unleash danger, spawning moving enemies and setting up simple encounters for the player to overcome. We've got a lot to cover, so let's jump right in. First up, we have player spawn points. We're using simple Node 2D nodes to mark specific X and Y positions in our game world. In this case, we use one to mark where the player begins their adventure. It's a great way to experiment with different starting locations during development. When the game starts up, the player will be moved into the level layer at this position. We'll use Godot's tile map system to build our 2D side-scroller world. Using the tile map node, we can paint tiles onto the grid like using a paintbrush program. Oh, and heads up if you're moving from Godot 3 to Godot 4, you'll notice that several relevant properties have moved out of the tile map and into the tileset resource. We could dedicate an entire series to the topic of tile maps, but for now, we'll cover the basics. A tile map consists of 2 crucial elements: the tileset resource that defines the available tiles, and the grid tile map that we will paint on. The tileset resource determines the shape and size of our tiles. In our platformer game, we'll use square tiles. You can also have multiple layers in a tile set that give you the ability to add some depth to your maps. However, we won't use those in our demo game. To add more visual effects to our tile set, we can also add different effects layers for different purposes. This allows us to assign more details to each tile in the tile set. Things like a collision shape and lighting effects can be controlled using these layers and allow each tile to handle its own lighting details. You can also add your own custom data sets to the tile set and tile map using these features. We'll use 2 main effects layers in our demo game. We'll use the collision layer property of the tile set to determine how 2D physics shapes will collide with the tiles. And we'll use the rendering occlusion layer on the tile set to determine how shadows should behave for the tiles. In addition to those layers, we also have the light mask on the tile set to let the engine know how the tile should receive and handle lighting effects. We'll look at those lights and shadows in more detail later on in this video. Let's look at the tileset editor in more detail. The DNA of a tile map is its tileset. The tileset editor is where you can configure tiles, set up regions and margins, and customize the tile data that will be available in your game world. You can then choose from the available tiles and paint them onto the tile map using this editor. The tileset editor can be intimidating at first, especially if you have a large number or differently shaped tiles. We're keeping things simple with a tileset that contains only 2 tiles. A simple empty tile, and a simple full square tile. The first thing we need to do inside a tile set is add tiles to it. We generally have an atlas texture that contains all of the tiles in a single image, and we can use atlases like that to populate the tile set. In our game, we have an atlas texture, tiles1.png, that's basically just the 2 tiles, one solid and one empty. We've already added those tiles to this tile set, but here's how we did it. Since our atlas is a grid of images, we can use the region size, margins, and padding settings during the tile import to get the exact tiles we want. If you're using a different atlas with different dimensions, these settings can be adjusted to match your grid. Then we selected the tiles from the atlas and added those to the tile set. You can add as many tiles as you want from as many atlases as you want to populate your tile set. Once the tiles are added to the tile set, each tile can be assigned additional information in their effects layers that we mentioned before. And here we'll add 2 important pieces of data to each tile. make sure you're in select mode in the tileset editor, and click on one of the tiles to see the additional data on the tile. For the physics layer 0, collisions are handled in the select tab under the physics section. Here, we'll give the solid tile a collision shape that covers the entire cell. This means that the tile will act as a wall or a floor. For the rendering occlusion layer 0, blocking light is handled in the select tab under the rendering section. Just like the physics collision layer, we'll give the solid tile an occlusion shape. In this case, it'll be a square that covers the entire cell. This will allow the tiles to block light and cast shadows. After the tiles are configured in a tile set with the appropriate layer effects, they can then be used to paint onto the tile map in the Godot editor. We only have 2 cells in our tile set, so making the level will be extremely easy for us. We can always add more complex tiles or change their settings at any time and place them into the game map as needed. And here's a little teaser. In the near future, we might delve into advanced features of the tile map system and maybe even create a separate auto tile tutorial for beginners. Stay tuned for that and let us know in the comments if it's something you'd be interested in seeing more of. Next up, let's shed some light on the game world using Godot's 2D light system. We already talked about basic lighting and shadows in a previous episode, but now we're going to expand on it using render layer names to make more interesting lighting effects. The 3 main node types to remember are light point 2D nodes make things brighter, canvas modulate nodes make things darker so that they can be brightened by the lights, and light occluder nodes that act like physical barriers that catch shadows from our light sources. By using a combination of these 3 concepts, we can make some interesting lighting effects with very little effort. Before we look at the nodes for those 3 concepts in more detail, and how they apply to our demo game, let's check the project settings and look at the friendly names we've given to each of the 2D rendering effect layers. We've named each rendering layer to match its purpose, and we've separated them out based on the type of object and if they represent a light or an occluder. The first layer is a default layer. For the simplest of games, everything can be on that layer, but we'll use these other layers to get some more complex lighting interactions in our game. The player layers representing lights and occlusion on the player node, the static layers representing lights and occlusion on the in-game objects, the tile map layer for lights and occlusion on the tile map tiles, and the background layer for lights and occlusion on the parallax background. We'll be using these layer names when we configure the lights, shadows, and occluders in our game. Using those names will make it much easier to remember what settings to use, and we can always add more layers if we need them. Okay, let's look at these 3 concepts in the nodes in more detail. The canvas modulate node can be used to add color tint to a canvas layer. We'll use these nodes to first darken our scenes to prepare those scenes so that they can be illuminated by light nodes. A canvas layer can only have 1 canvas modulate node on it. We've attached one here to the level scene. The important properties on the canvas modulate node are its color. To create light and shadow effects when creating shadows, this is usually a very dark color, but it can be adjusted as needed. And its light masks. These tell Godot which lights this canvas should respond to. Here are all the masks for the level canvas. Although it doesn't live directly in a level scene, we also added a canvas modulate node to our parallax background and to our player scenes. We'll be shining light sources from the level scene onto those scenes, so we'll use canvas modulate nodes to darken them first. We'll use these light masks for the parallax background, and these light masks for the player sprites. So now we have a darkened scene, and we can start adding in the light sources. The point light 2D node is used to create a light source that emanates from a specific point in 2D space. We discussed the basic properties of a light node back in episode 4, but as a quick refresher, the main settings of the lights are its texture or shape, the color of the light, the energy intensity, the layer ranges the light impacts, how the light should cast shadows, and the visibility and light masks. In the demo game, we have 4 categories of lighting. Each category will use different settings to get different lighting and shadow effects. This is an example of a static light that is off when the game begins. The light can then be turned on when the player uses a specific toggle switch in the game. We'll go into interactive player triggers in part 2 of episode 5. This is an example of atmospheric mood lighting. This can be applied to highlight the game in the backgrounds with different colors. We intentionally prevent these lights from interacting with some layers. This is a similar example, but in this case we have light casting shadows on additional lighters. Using this, we can create positional lights that cast interesting shadows and rays onto the game world. And here's a light that moves along with the boss projectile attack. More to come in the last video in episode 5 when we dive into the enemies and the scripted boss. Great, now we have a darkened scene that's being illuminated by our light sources. But we're missing the final piece of the puzzle. Without this piece, the objects and the tiles in our game won't cast shadows. We'll use Godot's Light Occluder 2D node and the concept of light occluders to block light and cast directional shadows in our game world. Occluders consist of a shape, a list of lights that they will interact with, and a few additional properties that affect the way the occluder works. There are 2 categories of light occluders in our level scene. Earlier in the episode, we talked about the tileset rendering layer, where each tile in the tileset can be assigned an occluder polygon. This is how the tileset will interact with our lights and cause the tiles to cast shadows. Here is the square shape occluder used on our simple solid tile and the light masks it uses. We use an Area 2D node to represent hazard tiles. This allows us to place the hazards in spots that are not 100% aligned with the tile map grid. In addition to a collision shape, these hazard nodes also have a Light Occluder 2D node on them. This node contains a polygon shape that will block light and throw shadows. We use these light masks on our hazard tile occluders. For visualization purposes, we made the hazard occluder slightly smaller than the hazard sprite itself, so that it can cast shadows slightly differently than the normal tile map tiles. You can see here how the shadow for the red hazard tile starts slightly inside of the sprite, unlike the tileset tiles that cast a hard-edged shadow. By creating occluders of different shapes and by combining them with lights and light masks, you can make for some interesting effects with very little effort. So now we can create tile sets and paint tiles onto our game map. We can make changes and add different rooms and challenges for our player to overcome. And we can add different types of lighting to our game world, some static and some more dynamic, some that cast shadows and rays, and some that simply give mood lighting to the scenes. Let's finish up with a quick recap of sound and audio. We saw how to use basic sound effects when we talked about the player scene in the last episode. Now we'll look at the audio on the level scene. Just like the player scene, we'll use Godot's Audio Stream Player node and raw MP3 files to create the sounds. The 4 examples of audio in the level scene are the sound effect for the player trigger when they use a key to unlock a gate. It's a simple sound effect that exists as part of the player trigger, and we'll see more of those in the very next episode. The background music for the level. Here's the background music that plays during the level. When the level starts up, we begin this track, and we'll replay it on a loop to keep it simple. The music and sounds that are for the big bad endgame boss. We'll fight that big bad endgame boss in the last part of episode 5, and we'll show how we script the battle in that video. But for now, here are 2 audio components for the boss battle. The background music that plays when they enter the boss arena, and the basic sound effect of the boss breathing fireballs at the player. And finally, we have the victory musical score. The final audio component on the level scene will be the music that plays when the player reaches the star at the end of the game. This is another sound that activates on a player charter, so we'll see this again in the next video. Don't forget to subscribe to our channel so you can get that episode as soon as it's ready. So far, in this first part of episode 5, we've learned some new concepts and expanded on concepts we've seen in previous episodes. We now have a basic understanding of tile maps and tile sets, and we can apply some interesting lighting and audio effects into our game world for different purposes. In part 2, get ready for us to add some text prompts, interactive switches, and items and power upgrades that can be picked up. We'll look at those and other player triggers coming soon. If you're just joining us, this is a series where I'm showcasing some of the basic building blocks that you can use to create a very simple Godot 2D platformer game. This is a beginner series, and we're not creating the next AAA blockbuster game here. It's more about playing with all the tools that are available to us and getting to see them in action in an oversimplified but practical way. If you've missed previous episodes, be sure to check out our development playlist on the Champ. In the last part of episode 5, we took our first good look at Godot's tile maps and tile scent editor, and we added simple lighting, shadows, and sounds to our game mat. Now we're going to bump it up a notch and add interactivity to the game world. We'll do this by adding the concept of player triggers into our level scene. By the end, we'll be able to create and duplicate many types of triggers and place them onto our level scene. We'll have some that add interactive switches for the player to toggle, some that show text pop-ups and hint messages for the player, some that open locked gates, and several that give the player awesome items and powerful upgrades that can be picked up. Let's get started. Here are the type of player triggers that we designed so far. We'll look at each one in more detail later in the video. Before we look at examples for each of these, let's talk about what a player trigger is, how they work, and the attributes that define them. A player trigger is our way of identifying designated points on the game map where the player can trigger an event or some sort of special action. First, this makes it easy for us to move triggers around on the map during our level design. The purpose of each trigger can range from mundane and repeatable triggers like a simple shop sign triggering an RPG that a player can activate to read the name of the shop, to one-time item pickup triggers that give players new powers and abilities in the game. All of these triggers extend the Area 2D node that defines where the trigger is on the map. Each trigger has two primary components, the sprite 2D to display on the game world, and the collision shape that will execute the logic for the trigger. Whatever logic that might be depends on the type of trigger. More on that in a moment. Some trigger types also have additional components, such as extra sounds, text panels, and Node 2D nodes. We'll see those when we get to the trigger types that use them. Another important note that is that most triggers fall into one of two main categories. Either they are item pickup triggers, where the player will receive a one-time buff or a permanent upgrade like an item, or they're not related to collectible items and instead add more interesting things to encounter in the map. Okay, let's look at some of the trigger types and what they do. We'll start with the basic prompt trigger. Using this trigger allows us to pop up text messages for the player. Useful for area names, titles, signs, tips, and other quick pop-ups. This trigger and several like it contain an additional node that holds a UI panel and a text label that will be displayed to the player. Next up is the heart item pickup trigger. Bet you can't guess what this does. There's nothing special about this trigger other than it's a pickup style trigger, and it'll only activate one time when the player collides with it. We can duplicate and place as many of these heart pickups as we want. We have 2 on the map right now. The third trigger type is a toggle trigger. This works very similar to the prompt trigger in that it has a panel and a label that'll be displayed to the player. However, this trigger does not activate until the player presses a button on the gamepad. We also have this trigger connected to a signal that will turn a light on and off in the map when the player presses that button. The next trigger type is the boots item pickup trigger. Like the heart upgrade, this trigger deactivates once it's used once. However, in this case, instead of healing health points, the player is awarded with the speed boots upgrade. When the player has this upgrade, they can use a button on the gamepad to sprint much faster than the normal walk speed. This will give the player the ability to traverse areas more easily and make longer jumps to access previously inaccessible areas. Now let's look at the portal trigger type. As the name suggests, this trigger teleports the player somewhere else on the map. We have 2 of them on the demo map. Each one has a Node 2D node that determines where the player will go when they use the gamepad to activate the portal. They also have a text pop-off component, and will only activate when the player activates them, much like the toggle trigger. The lock and key trigger types allow us to create a secret passage on the map. This is an example of multiple triggers coming together to create a more complex interaction. The player must first obtain the key by activating the key item pickup trigger. When the player uses that key at the lock trigger, it'll open up the secret passage on the map, allowing them to explore deeper into the game. The lock trigger is also an example of a trigger that is accompanied by a sound effect. This audio is played when the secret wall is opened. The next 2 trigger types are upgrade pickup triggers, and much like the boots, they will permanently upgrade the abilities of the player. With the shield trigger, the player will pick up a shield upgrade. This immediately sets their health to 10, making it much more durable. And the pistol trigger, as you might have guessed, gives the player the pistol upgrade. Once equipped, the player can use the gamepad to fire their pistol. We'll see some more details on that weapon and its projectiles in the next episode. And finally, the last trigger type is the star trigger. This is the end goal of our simple demo game. When the player reaches this trigger, the game ends and they are presented with their final score, the time it took to reach the princess head, the star at the end of a map. Now that we know what each trigger does, we can add them to our game map and move them around as desired. Now let's look at some of the logic and code that handles the player triggers. All triggers show the same underlying code that manages how the triggers are initialized and how they are activated. The triggers rely heavily on Godot's signals to communicate data, from the trigger back up to the level scene. This code in the level script is responsible for initializing all of the connections so that they'll execute the correct logic depending on the type of trigger. Each trigger in the level is assigned a script that controls how that specific type of trigger behaves in the game. To assist with connecting so many signals, we used a simple array mapping in the level script. The initPlayerTriggers function will connect the signals to the level. Most trigger types will emit at least one signal that we'll listen for and handle in the level script. Several of the more complex trigger types use more than one signal, but overall the concept is the same. We're connecting the signals from each of those trigger instances found on our map to the functions in our level script. In some triggers, we'll also keep track of when the player enters or leaves the trigger area. And in other triggers, we'll give the player a permanent item or upgrade when they collide with the trigger. And yet, in other triggers, we'll wait for the player to interact first before we perform some action. By being creative and mixing these concepts together, we can create some fun interactions in our game and give the player a sense of agency. It also makes it easier to add new triggers and trigger types to the level scene, since the main plumbing is already hooked up. And that covers how we use player triggers in our level scene. We can add multiple layers of interaction for the player, from simple text pop-ups to giving them health and items, and upgrades to give them new weapons and movement abilities. In the final episode of the series, we'll throw out some ideas on brand new trigger types that you could add to the demo, like new items and upgrades for the player to interact with. But before we get there, we're going to finish up episode 5 with one more video where we'll add hazards, moving enemies, and the basic combat mechanics to the demo game. And finally, we'll close out this episode with a scripted boss battle to give the player a finale. Hi there, welcome back to the series. In this final chapter of episode 5, we'll explore the concepts of hazards, combat, and enemies. We'll look at creating some environmental hazard tiles that damage and stagger the player on contact. We'll create enemy objects, make them move back and forth, and place some enemy spawns around the map. We'll look at the player's main attack in the game, and at the end, we'll even add a scripted boss battle. Here's how we implement simple hazard tiles that cause the player to stagger and take damage, adding a basic layer of challenge to the gameplay. We can duplicate and make as many of these hazards as we want. Each hazard tile is an Area 2D collidable node. Each one contains a sprite, its collision shape, and a light occluder. These hazard nodes connect to the main code using the body entered signal. Here's the simple code that runs. When a body such as the player character enters the hazard area, it takes 1 damage. Note here that we should probably be checking that this body actually has the damage function we're calling, otherwise an error is likely. For now, we'll assume it always has the take damage function. Taking damage, if you recall back to earlier episodes, causes the player to enter a temporary stagger state. In this case, the player character is pushed back and away from the hazard tile while taking the 1 damage. During this window, they cannot take additional damage and they have no control over the character's movement. Taking damage and being staggered happens in other ways too. Another common way for the player to take damage is a collision with an enemy. Let's look at an oversimplified enemy. This little monster doesn't think much. It just moves horizontally until it hits a wall and turns back around. The enemies in the game are barely enemies. They're actually kinda cute. But these little guys can damage the player if they're touched. This causes the player to stagger like normal, making them an additional challenge when paired with other platforming puzzles. We start with a new scene, the enemy scene. It has its own script and several child nodes that hold stats, a sprite, and a collision shape. In this enemy scene, we focus only on the features that are important to our little moving monsters. This will keep the code more organized and make it easier to understand by separating the entity code from our player and level code. Let's look at the 3 scripts for the enemies. We'll check the enemy stamps class first. This uses the same signals that we used for the player stats class back in episode 4. This class gives the enemy a health pool, as well as the required functions to heal and take damage. Using a component class for stats like this allows us to more easily add new types of stats, like a mana pool or ammunition count, later in the game design process. Those signals and functions will be used by the next class. This is the enemy base class based on the Area 2D node, and it contains the bulk of the logic to control health, damage, and collisions for the enemy. In the ready function, we see how the stat signals are connected, and we can see the various functions that will be called when those signals are fired. These enemies can collide with two different types of objects, bullets and the player. If a bullet touches an enemy, they'll take damage. If a player touches them, the player takes damage and is staggered back. The final class is the enemy class, which extends the enemy base class. This is the class that will go into our level scene for each of the enemies we want to create. It gets all of the features of the enemy base class, like damage and collision handling, but then it also keeps track of the direction the enemy is moving and allows it to turn around when it hits a wall tile. And that's it for the simple moving enemies. Those three scripts control the life cycle and capabilities of a single enemy. Now we just need to create some enemy nodes and place them into our level scene. To keep the node tree organized, we grouped all of the enemy nodes together under a single enemies node. We also nest them in a simple node 2D containers where each spawn point holds a single enemy node. Later, we could use this to respawn enemies or spawn multiple enemies from a single point. We have 4 enemies in the level, and we can add more anytime. Besides just jumping over enemies to avoid them altogether, there is another way that the player can defeat the challenges that these little monsters present. The player will get a pistol during the course of the level. That gives them the ability to fire projectiles which, when they hit an enemy, it will cause the enemy to take damage and possibly die. Let's look at the player's projectile logic in more detail. With the pistol equipped, the player can use the gamepad to fire their weapon. For now, the player can fire simple projectiles that will only move horizontally. We can add more directions later. We'll also set it up so that only one bullet can be active at a time, and we can change that layer as well. The bullet scene is the node for the player's bullets. Like other scenes, it contains a few child nodes, mainly a sprite and a collision shape. The bullet class script is where we'll handle all collisions by the player bullets. It will also only allow one bullet to be active at the same time. It extends the Area 2D projectile class that defines the core properties and handles the main physics for all projectiles. These include properties like the bullet's speed, its damage value, and the direction it is heading. The player script is responsible for firing the bullet in the direction the player is facing. We preload the bullet scene and instantiate new bullets as needed. When a player bullet flies with a wall, the projectile will be destroyed. If it hits an enemy, the enemy will take damage and possibly be defeated, and the projectile will be destroyed. It'll also damage the boss. Speaking of the boss, the simple enemies so far don't fire projectiles of their own, but the boss will. Let's finish up by looking at the scripted boss battle and how it differs from these normal enemies. The boss consists of a bunch of parts working together to provide a more complex battle for the player. It's still a very simple example, and there are many ways that we can improve it later. Since we just covered the player projectiles, let's look at the enemy bullet class first. This enemy bullet class is very similar to the player's bullet class, except it's used by the custom boss script instead of the player script. We'll see that boss script in a moment. The enemy base class handles collisions between the player and the boss's breath weapon. If the player collides with an enemy bullet, they'll take damage. The class extends the same projectile class that we just talked about and has the same basic physics properties like speed, direction, and damage. When we look at the boss script in a few seconds, you'll see how we make the boss fire their breath weapon. The physical shape of the boss consists of several collision shapes all combined together. These boxes are overlaid over the boss sprite. Next, we'll use an Area 2D to cover the entire boss zone. The zone uses a simple script with collision signals from this area to trigger the boss script events and activate the boss battle music. We'll store the boss health in a stats component just like we do for the other enemies. And here we'll set its max health to 50. This boss area also has a UI panel and a label so that we can see the boss health. In many games you wouldn't see the numbers here, or maybe you'd see a big health bar across the top of the screen. Now that we've looked at the building blocks of the boss battle, let's look at the script that pulls it all together. First, we preload the enemy bullet scene, and we'll create duplicates of this whenever the boss is breathing fire at the player. In the physics process, we check if the boss zone is active and if we should start or stop the boss battle music. In the ready function, we'll connect a timer on the boss breath weapon. Each time the timer times out, it'll cause the attack function to be called, where we'll pick a random angle to fire and instantiate a new enemy bullet. If the player collides with the boss, they'll take 5 damage instead of the normal 1 damage that a regular enemy does. We also handle the player doing damage to the boss using their pistol, and destroying the boss encounter after the boss reaches 0 health. And when we put it all together, it looks like this. It's not the most satisfying boss battle in the world, but it's more engaging than our regular enemies, and it is a bullet sponge. We can definitely improve on it over time. In Episode 5, we worked our way through the core building blocks of creating the level scene in a 2D platformer game. Starting with the foundational elements of the tile map in the tile set, incorporating basic lighting and shadows, and playing audio to bring game world to life. As we progressed, we introduced dynamic player triggers, from simple interactive switches to power-ups and item pickups, and conclude with the exciting addition of hazards, enemy spawns, and now a boss battle, all enriching the gameplay experience for our demo game. I hope you found this episode helpful. In Episode 6, we'll outline a number of potential features for a hobby game developer to experiment with in their own Godot projects. From new weapons, player triggers, and enemies, to advanced concepts like room transitions and leveling systems. We'll also talk more about concepts of coding standards, source code control, and using resources in Godot. It's all about unleashing your creativity and exploring the possibilities in game development. Here's what you end up with when building your first 2D platformer game using the Godot tutorials on our channel. Over the course of those 10 videos, we show how the nuts and bolts of a simple game come together to create a basic 2D platformer. The project is running in Godot Engine 4 and uses GDScript. It'll be available on GitHub soon. If you want to see more microgame tutorial video series like these, be sure to subscribe and drop us some comments. Maybe a twin-stick shooter or a puzzle game? How about a simple RPG adventure or a mini tower defense? What do you think?